In the last video, we defined these matrices that are called elementary matrices, which are matrices that are generated by way of performing one elementary row operation on the identity matrix. And we messed around with those a bit. We had said that it wasn't a nice, efficient way to maybe solve problems and mess around with matrices, but there was an idea about the structure of the matrices themselves that we were looking for. And we then said we could take these matrices and take some matrix and multiply it by an elementary matrix and see what happened. We multiplied by the chain of elementary matrices to see what that would do to some other matrix. And now we want to kind of look at some of the theorems and ideas that fall out of all of that work we did with elementary matrices. So first off, we have this idea called row equivalence. Let A and B be n by n matrices. B is row equivalent to A if, I don't like if, when there exists, remember the backwards capital E, there exists a finite number of elementary matrices E1, E2, out to En, such that, remember, backwards capital E means there exists, backwards curvy E means such that B is equal to EK dot EK minus 1, E2, E1 dot A. And the idea, I don't want to go through the whole example of games we did in the last video, but we had matrix A, which was equal to 1, 2, 3, 4. We then performed a bunch of row operations and got it to the upper reduced row echelon form 1, 0, 0, 1, which we can call matrix B for the purposes of this. We then created the elementary matrices. I'm not going to write them out, but there were 3 of them. And we said that B, this matrix, we could get by multiplying the elementary matrices on the left times my original A. This means that A and B are row equivalent because there's a finite number of elementary matrices, E1, E2, and E3, that I can multiply by A to end up with B. Again, keep in mind from a notational standpoint, you have these matrices E1 out to some En. When you multiply them in reverse order, E1, E2, EK minus 1, EK, etc. So just be aware of that notationally. But yes, we have this definition now, but in the last video, we actually worked with it and saw what was going on, so the definition should make sense. But now we can get some theorems out of it. So first off, if E is an elementary matrix, then E inverse exists and is an elementary matrix. As far as the proof goes, again, this one we don't really need to prove. It should be pretty clear what's going on here. If I have an elementary matrix, then that's by definition a matrix that essentially I took the identity and I performed one row operation on it. Now I know that I can multiply by those elementary matrices. But clearly, based on row equivalence and my understanding of the multiplication from the last video, I can multiply and kind of get back to where I started, which was my identity matrix. So clearly I should be able to take an elementary matrix and multiply it and end up back with the identity. That one should be clear. If it's not, that's one that I want you to work through on your own. Again, it should be pretty straightforward. The idea makes sense. But from that, we get this. A square matrix A is invertible if and only if, remember IFF means if and only if, it can be written as the product of elementary matrices. And now, just make sure we're clear. If you have seen this before, that's good. If not, just so we're clear, this IFF right here means if and only if. Essentially, it means that's a two-sided theorem, or I guess a two-sided proof to prove the theorem. What you have to show is, if you have a square matrix A that's invertible, then it can be written as a product of elementary matrices. And you have to go in the other direction. If you have a square matrix A that can be written as a product of elementary matrices, show that A is invertible. So really quickly, as kind of like a more or less rough sketch of the proof that will work, suppose I want to go this way. So suppose that A is a square matrix and A inverse exists. Ergo, it's invertible. I need to show it can be written as the product of elementary matrices. But let's see. If I go back to one of my earlier theorems from the beginning of this chapter, I think we had shown that if AX equals 0, then the only solution is the trivial solution, where all the x's are equal to 0. Which again, if you think about it, if you're not entirely remembering everything from the beginning of this chapter right now, it's A is invertible, so the inverse exists. Just multiply by the inverse on both sides, and you get x equals 0 or something times 0, which will still be the 0 matrix. So that makes sense. It's straightforward. But what that means is, if I think about my augmented matrix, for right now, since A is arbitrary, I'll just say A0, where that's my A matrix, this is my 0 column vector. I know the solution, the only solution is the trivial solution, which means if I take A, and since it's invertible, multiply by A inverse on the left, I can rewrite this as I0. Because again, A inverse times A will give me the identity, 0 times anything times 0 will still give me 0. But now let's see. Well, it can be written as the product of elementary matrices, but if we think about my row operations, essentially what I did was I took the matrix A and I rewrote it as the matrix I. But how do I turn matrix A to matrix I? I perform row operations. Admittedly, I can think about this in terms of multiplying by the inverse. The other way to think about it is in terms of performing the row operations. But if I perform the elementary row operations, then I know all that really means is I just multiplied by a chain of elementary matrices, which are the same as performing the row operations. Which means, clearly, A can be written as the product of elementary matrices. Because that's what it means. That's how I get from here to here. So this part is done. Again, it's pretty straightforward. It's just based off of the definitions that we already know. Suppose I want to go this way. So suppose that A can be written as EK, EK minus 1, and so on, E2, E1. So suppose A can be written as the product of elementary matrices right here. I need to show that it's invertible. But all of these are elementary matrices. If E is an elementary matrix, then E inverse exists and is an elementary matrix. Which means each of these has an inverse. And if I multiply, say, the inverse of each of these together, well then by definition, the product of invertible matrices, I have to say the grammar they're correct so I have to think about it. The product of invertible matrices is an invertible matrix, which means A is invertible because this is invertible. Which is nice and straightforward and works really well. And again, I do stress from a proof perspective, again, that's just pretty much definition. Some of these proofs are really straightforward applying definitions. Other ones, like a few we did earlier, you can solve algebraically out. A few we solved use like the associative property, the commutative property, things like that. Other times they're more operational in nature. We have to perform a lot of algebra beyond just basic associative distributive property, things like that. You will get a bunch of these for homework. I try to find a few each set of homeworks for you to work on. Again, just so you can see the different types of proofs we do and think about, well, okay, how would I actually go about solving that? Can I solve this using algebra? Can I solve this using a general matrix that I just create? Can I solve it using definitions that I know? And that's one of the goals of this class, to be able to think about these theorems and come up with ways to prove them, which is why we go over them and which is why I let you go through a bunch of them in your homework, because it's worthwhile to do. But now we begin to see there is kind of this relationship between, well, there's clearly a relationship between the identity matrix and elementary matrices, definition. Now there seems to be a relationship between elementary matrices and inverses. So what else can we get out of that? And we get one more theorem. If A is an n by n matrix, oh no, I'll write it this way for now. The following are equivalent. And just for future reference, my brain doesn't even want to write that. The following are equivalent. My instructors always abbreviated TFAE because they didn't want to write all that out. So in the future, if I randomly write TFAE, it means the following are equivalent. It's not like true, false, or anything like that. my brain automatically wants to write TFAE, so I am sure at random points throughout the semester I will do that. So just be aware, it means the following are equivalent. 1, A is invertible. 2, AX equals B has a unique solution for all n by 1 column matrices B. 3, AX equals 0 has only the trivial solution. 4, A is row equivalent to I sub n, the identity. And 5, A can be written as the product of elementary matrices. If A is an n by n matrix, the following are equivalent. And from a proof perspective, if you were to prove this, you would essentially have to prove that everything implies everything else. So 1 implies 2, 1 implies 3, 1 implies 4, 1 implies 5, etc., etc., etc. I'm clearly not going to do all of that. Although some of these we have already proven, or they're essentially trivial, meaning, well, let's see. The last theorem we just had was a square matrix is invertible if and only if it can be written as a product of elementary matrices. Which means if it's invertible, that implies it can be written as a product of elementary matrices. So that's done. If we assume AX equals B has a unique solution for all column matrices B, then clearly this can only have the trivial solution. We understand that I can write these things as products of elementary matrices. If I'm row equivalent to the identity, well then I'm clearly invertible because I can just write out my product of elementary matrices, which will then turn into my inverse like we saw like 10 minutes ago. So again, there is a relationship here that should be pretty clear to see. And a bunch of these equivalencies we have already shown in one direction or the other, or in some instances both. Now we just kind of have them all together. And essentially what it means is, on a problem, if you have an n by n matrix, if one of these is true, if you can show it's invertible, then you get all of this automatically. You can say, okay, this matrix is invertible, so it's row equivalent to the identity. Or AX equals 0 has the unique solution, and the trivial solution, which is unique. So it's really powerful. Essentially, getting one of these 5 immediately gets you all 5. But to see how it works, let's see. For the purposes of this, since I'm assuming you all have it written down, I'm going to have to erase this. But the one I wanted to show was AX equals B has a unique solution. So just to work with that one really quickly. So, suppose I have we'll go back to the standard, 1, 2, 3, 4. B is equal to 0, 0, my 0 column vector. AX equals B just means 1, 2, 3, 4 times x1, x2 is equal to 0, 0. And I would point out, A is clearly invertible. You can find the inverse. I'm pretty sure we've actually done it before because this is not in one of the other videos. It's invertible. So then, according to that theorem we just wrote out, since it's invertible, this AX equals B should have a unique solution. And in this case, if B is equal to 0, 0, the solution should be unique, and it has to be the trivial solution 0, 0. So, just to kind of work through that, to see that the fact that A is invertible allows us to show that all this is true. Well, okay, I have that, and now again, first, clearly, x sub 1 equals x sub 2 equals 0 is a solution. If those are both 0, when I do the multiplication, I'll get zeros and I'm good. Now show that that is unique. So, well, let's see. I want to write out the form I did. If I write out my augmented matrix, well, let's see, my augmented matrix will be 1, 2, 0, 3, 4, 0. Now, in this case, just perform the row operations here. I won't bother finding elementary matrices or anything. If I do that, the top row will stay the same. Multiply the top row by -3, add it to the bottom row. -3 plus 3 is 0. -3 times 2 is -6 plus 4 is -2. -3 times 3 is 0 plus 0, which is 0. Now I have 1, 0. So now top row will stay the same. Multiply this row by -1/2. 0 times -1/2 is 0. -2 times -1/2 is +1. 0 times -1/2 is 0. Now, multiply this row by -2 and add it there. Bottom row will stay the same. -2 times 0 is 0 plus 1, which is 1. -2 times 1 is -2 plus 2, which is 0. -2 times 0 is 0 plus 0, which is 0. But now I get my solutions. x1 equals x2 equals 0. Which means this is the only solution that I get. And again, this is kind of the idea. Now, I don't even need to perform these operations if I'm trying to solve a problem out to find the x sub i's that are my solution. Then yes, I would still have to perform these operations as of right now. But in general, I can say, I have this matrix. I know it's invertible. Since it's invertible, I know this will have a unique solution. I know if b is equal to 0, that solution is trivial. And I don't have to really think about it. I can just assume it, because one leads to all the others. I would also point out, I deliberately did this for the 0 matrix, the 0 column vector. But if I changed this to something else, just say b sub 1 and b sub 2, all that would really change is these values on the right as I multiplied and combined different rows together. But then ultimately, I would get something. Right here, I'll say b sub 1 hat, because it'll clearly be different than this original one. But then I would still get x sub 1 equals b sub 1 hat, x sub 2 equals b sub 2 hat, and that solution would still be unique. So the algebra here makes it pretty clear what's going on. And again, if you wanted to prove this out, you could prove it in general algebraically. Make this even more general. Call this a sub 1, 1, a sub 1, 2, a sub 2, 1, a sub 2, 2. Then do all the operations out, all the row operations, and get your solution that way. But we don't really have to now. We can just say, that's invertible, there's a unique solution. And again, if I wanted to then find that solution, then I would actually perform the row operations on the matrix I was given to get the solution. And I do point out, this is actually all the stuff you've already been doing throughout chapter 1 and chapter 2. Now we're just kind of formalizing it and saying those things that we have been doing, the operations that we have been doing to solve systems of equations out, now I can be confident that in certain situations, those solutions are unique and those tricks that I have been applying will work for any problem, as long as I meet certain criteria. Elementary matrices, invertible matrices, things like that. We are going to continue with this. Like I said, there's one more little thing in this section that I want to go over, but these videos with all this stuff on them get rather long. So I'm going to save that and make a video on that, as well as on the last section of chapter 2 tomorrow. And as I said in the last video, if it turns out that the amount of homework you have with the exam is simply too cumbersome to complete this week, let me know and I'll just push your homework due date to next week, because I know there's a lot to do this week.